Hey folks, in this video we're talking about calorimeters and the heat of reaction. My lord, let's get into this goodness. So I want you to be able to define calorimeter and also calorimetry. I want you to be able to explain what a calorimeter is used for. I guess that's part of this. And I want you to be able to define heat of reaction, which we're also going to call enthalpy of reaction. And we've talked about enthalpy before. Neat. Calorimeters and calorimetry. Well, calorimetry is the act of studying the heat that is absorbed or released during a chemical reaction or a physical process. Those things are different. So chemical reactions are going to typically either absorb or release heat. Absorb or release that heat. And so an example of that would be like a combustion reaction, fire. And that releases heat. You know, you get hot if you stand near a fire. The heat of reaction, also called the enthalpy of reaction, is the heat that's absorbed or released during a reaction. That makes sense. It's nice to call it heat of reaction, but enthalpy is a better word. We're going to use that later. So cool beans. A physical process, this would be stuff like melting or boiling or dissolving. That is also going to absorb or release heat. And it's important to make sure that we can distinguish between physical processes and chemical reactions. So like if I had boiled this water, it would still be water. The chemicals in it would not have changed. So that's a physical process, not a chemical reaction. So like you melting stuff, that's going to absorb heat. You put an ice cube in your hand, it starts pulling heat out of your hand. Or we would also call that the heat of fusion, which I don't know why they called it fusion for melting. It's dumb. But that's the science that we've got to go off of. So heat is either absorbed during melting or released during freezing. Neat stuff. Boiling is another physical process, and that absorbs heat when something boils. We have to add heat to something to make it boil. This is we're going to define that as the heat of vaporization, and we're going to use that for when things boil or condense. So heat is absorbed during boiling, the heat of vaporization, and it's going to be that same amount of heat that's released when that chemical condenses. Neat stuff. Heating and vaporization, the same amount of heat to go either way. Same thing with melting and freezing. And so dissolving may either absorb or release heat. We're going to actually study that in the laboratory. Neat. So a calorimeter is a device that somebody performing calorimetry would use. A calorimeter is a device that you use to measure the heat that's absorbed or released during chemical reactions and physical processes. So a calorimeter is the device used in calorimetry. Neat. And so chemical reactions or physical processes are going to take place inside that calorimeter. And a lot of different things can be used on its calorimeters. More on that soon, though. So there's many different types of calorimeters. Soon as now. There's a simple coffee cup calorimeter, which we'll use in a chemistry lab. And that's just a coffee cup with water inside of it. And that is the system that we're going to study. We've talked about systems before. The system would be the coffee cup and the water. Another cool thing is a bomb calorimeter. That's things where actual explosions can take place inside of it. And the volume of it doesn't change. They're neat things. We won't use those because they're pretty fancy. So the heat change in the calorimeter is going to be the opposite of the heat change for the reaction. So if that reaction releases heat, your calorimeter is going to absorb that heat. Or the reverse, if your reaction absorbs heat, that heat's going to come out of your calorimeter. And so we can simplify this into an equation where Q for our calorimeter, the heat of our calorimeter, is going to be the negative, or the heat exchange in our calorimeter is going to be the opposite of the heat exchange for the reaction itself. So calorimeters typically have their own specific heat. That's nice to know. And we're going to refer to that as C-cal, specific heat of the calorimeter. So we can write a nice simple equation here where Q for the calorimeter is just going to be equal to C for the calorimeter times the change in the temperature in that calorimeter. A nice simplified version of our Q equals MCAT because the calorimeter has a specific mass and it works in a specific way. So we simplify M and C into just C-cal. Neat. So by using Q of the reaction and the moles of chemicals that were used, we can determine the heat of the reaction. So if I know how many moles react and how much heat they release, I can learn the heat of the reaction. Neat stuff. We can also call this enthalpy of the reaction, as I said earlier. And that's the amount of heat that's either absorbed or released when 1 mole of a substance undergoes a chemical reaction or physical process. This is typically going to be measured in kilojoules per mole, kilojoules of heat release per mole of substance reacting. Neat stuff. And we can also call this heat of reaction, which we've done before, but enthalpy of reaction is a better phrase for that. More science. So feature in little practice. Let's do some of that. We got 55 grams of sodium nitrate, and that's dissolved into a water inside a calorimeter. What is the heat of solution for this sodium nitrate if the calorimeter cools from 25 degrees Celsius to 10 degrees Celsius? And we know C-cal for the calorimeter. So we're going to do this kind of similar to how we would do a reaction, a typical, where are my words at? Q equals MCAT, except we're going to use Q equals C-cal. So first we're going to determine how much energy that calorimeter absorbed, or I guess didn't absorb it, it released. And therefore we can figure out the Q of the solution, because we know those are opposites. And if we use this Q of the solution and the moles of sodium nitrate, well, we can go ahead and figure out the delta H of solution, heat of solution here, or enthalpy of solution. Anyway, let's show how we're going to do that. So for step one, we got to figure out Q for a calorimeter. And that's pretty simple. We know this basic equation, Q-cal equals C-cal times delta T. Well, delta T is final minus initial, so 10 minus 25 times that C for the calorimeter. And that gives us a fancy negative 12.66 kilojoules. All right, sweet stuff. So then from there, what are we going to do? Well, we know that Q-cal is opposite for Q of solution. So we know how much heat that solution released. But we want to figure out how much heat it is per mole of sodium nitrate if we're going to get this delta H. So we need to figure out our moles of that solute, that dude who gets dissolved, the sodium nitrate. So sodium nitrate, we know it's this guy, and my text box came in here a little bit weird, but it's supposed to say NaNO3, sodium nitrate, is equal to 85 grams per mole. So we've got our molar mass. And now we can take our grams, and we can convert that into moles. Nice. This problem's a little spicy. So now that we've got our moles of sodium nitrate, we can figure out delta H, because we need the heat per mole. And we know the heat that the solution absorbed, it's positive. And we know the moles, so we'll do our heat divided by the moles. Let's plug that suckers in. So we know delta H of the solution is approximately 19.5 kilojoules per mole. When you dissolve sodium nitrate, you can expect that dude to absorb some heat, 19.5 kilojoules of heat per mole of sodium nitrate. All right, let's check out this problem. We got 86 grams of zinc, this guy, that reacts with HCl, hydrochloric acid, according to the following reaction. Neat. The reaction takes place in 56 grams of water. What is the temperature change of the water if we assume all heat released by the reaction is absorbed by the water? All right, and so we know the specific heat of the water, and we know the heat of the reaction. Neat. Why don't you try this problem out? Cool, you tried it out. Let's try it together. So what are we going to do here? Well, I know this guy here. I should figure out what the temperature change for this is. Okay, so I should figure out then how much heat is released. If this is kilojoules per mole, I'm going to need moles. I can change my grams of zinc into moles. Cool. And then I can figure out the heat that's released by the reaction, and that should tell me how much heat's absorbed by the water. And then I can use MC delta T to figure out the temperature change of the water. Nice. Q equals MC delta T. So yeah, I'm going to use this guy. I don't know why it says salt. It should say water. But we're just going to say sol for solution. And so, yeah, I know 56 grams. I know the specific heat, but I don't know the temperature change. I want that. And I don't know this guy. But, as I said, I can figure out this guy, how much heat is absorbed by my solution, if I figure out how much heat is released by the reaction. And I can figure out how much heat is released by the reaction by using my heat of reaction, enthalpy of reaction, if you want to call it that, and the moles of zinc. But I gotta get the moles of zinc, so I'll use the mass of zinc, and I'll do some X-line magic, and the conversion factor I'll use the atomic mass, or molar mass of zinc. And so I can do some sweet maths and come up with, all right, 0.86 grams. Well, that's the same thing as 0.013 moles of zinc. And now I can plug those moles in with this guy. I can use my moles in this, because this guy's got moles in it. So if I multiply this by moles, the moles will go away, which is what I'll do. And I'll end up with, all right, it's going to release, if this many moles of zinc react according to this reaction, we should get approximately 1.05 kilojoules of energy released. negative 1.05 kilojoules will be the heat exchange. And so all of that's going to get absorbed by the solution. The opposite of this should be the heat absorbed by the solution. And so, all right, I got to convert my kilojoules to joules. I should know that there's 1,000 joules in a kilojoule. Kilo means 1,000. And so now I can plug this dude into Q and figure out delta T. Oh, let's do it. Let's do it up. Bam. And then we can simplify those guys, divide over, and get our delta T, our heat change. Temperature change should be 4.5 degrees Celsius. Our water should get a little bit warmer because this thing's going to get hot. Anyway, that's the end of this video. I hope you understand a little bit about calorimeters and calorimetry, why you would use a calorimeter, and how you would do that. Ta-ta. Have a great rest of your life.